Hi, welcome to the fourth step in our proof that pi is irrational. In it, we push algebra literally to the limit. This is the meatiest part of the proof, but I'll do my best to make it easy to follow. After last time, where we saw how a quotient of power series can be converted to a continued fraction, we apply the method to the power series we've established for the sine and cosine. This will yield a formula for the tangent of a number x, in the form of an infinite continued fraction. Let's get started. First we factor out x, then the series in the numerator looks very similar to the cosine series. Remember that we represented the power series with a bar diagram. One bar for each order of x. We'll do the same here, but instead of using 1, x, x squared, x cubed, and so on, we are only dealing with even powers of x anyway. Let's also include the alternating sign into the column headers so we don't have to draw bars with negative height. The upper series in this representation has coefficients 1, 1 over 3 factorial, 1 over 5 factorial, 1 over 7 factorial, and so on. The lower series is represented by bars of height 1, 1 over 2 factorial, 1 over 4 factorial, 1 over 6 factorial, and so on. When we go through Euclid's algorithm, the bar heights will become very small very fast, and their values will be cumbersome fractions that make the pattern hard to see. Instead, we will focus on the ratios between them. The coefficients in the upper series are connected by factors 2 times 3, 4 times 5, 6 times 7, and so on, and multiplying them by 1, 3, 5, 7, and so on, respectively, gives the entries of the lower series. The first fitting goes from top to bottom. This gives us an integer part of 1. This changes the middle multiplying factors to 0, 2, 4, 6, and so on. Shifting the leftover series to the left amounts to factoring out minus x squared. When you look at the arrows, you'll notice that the leftmost bars are connected by a factor of 3. The next pair to them by a factor of 5, then 7, and so on. Likewise, we can complete the lower series with factor arrows 2 times 5, 4 times 7, 6 times 9, etc. This information allows us now to perform the next fitting. But it now goes in the other direction, that is, we are decomposing the inverse ratio. The integer part is 3, and subtracting this from the middle factors leaves us again with a sequence of even numbers 0, 2, 4, 6, etc. Divide by minus x squared, and let's look at the factors again. The first two entries are connected by a factor of 5, then 7, then 9, and so on. At the top, the ratios between the bars are now 2 times 7, 4 times 9, then 6 times 11. Now the setup is ready for the next subtraction. This time we can fit the upper row of bars 5 times into the lower. The middle factors become again the even numbers. Then we divide by minus x squared and complete the factor arrows. The next fitting is done with the leading factor of 7. At this point the pattern becomes visible. We extract precisely the odd integers. After 7 comes 9, then 11, 13, etc. Each of these steps is a simple algebraic transformation, but taken together they are quite a beast. But the representation with bars and arrows makes the pattern more apparent than traditional notation would. We therefore arrive at this expression for the tangent. Let's reflect on what it means exactly to have an infinitely nested fraction on the right. Strictly speaking, we can only calculate approximate values of it by cutting off the nesting at some point. This gives us a function that is a good approximation for the tangent, but it breaks down as x strays far away from 0. The more layers we retain in the continued fraction, the better the approximation, even for larger values of x. There's a link in the description to a Desmos page that plots the different approximants. This is an immensely astonishing result, and we have proved it by going to the limit of what's possible using just the 4 basic operations of algebra. Now we are on the finishing line. In the last step, we show that this expression is indeed irrational for rational values of x, and the irrationality of pi will follow. See you for the grand finale.